Have you ever looked up at the night sky and just felt this profound sense of wonder? Maybe that nagging question. Are we really the only show in town?
Uh-huh.
For centuries, that was pure speculation, right? Stuff for philosophers, for dreamers, but we'll hold on tight because things have seriously changed.
Absolutely. The moment we started actually finding planets circling other suns,
Yeah.
these exoplanets, that philosophical pondering,
Hmm.
it just sort of slammed into the world of hard science.
Yeah.
It's not just what if anymore. Now it's okay. Let's look at the data.
And wow, is the data pouring in? Since the mid 90s, it's been this explosion of discovery. We're talking an exponential leap
That's correct.
in the number of known exoplanets. And it's revealing this unbelievable diversity of planetary systems
Hmm.
just right here in our own Milky Way. Seriously, it kind of bends the mind.
Exactly. And that ever expanding catalog, that huge collection of worlds, well, that's the essential ingredient, isn't it?
Right.
It gives us the sheer numbers we need to get serious about investigating, the potential for life beyond Earth.
So, no more just guessing at cosmic possibilities. We're actually out there finding places, and we're using real science to figure them out.
Hmm.
This deep dive is going to be laser focused on those potentially habitable exoplanets, right?
Yeah.
We're going to dig into what it truly means for a planet to even be considered a contender for life based on, well, what we currently understand.
Precisely. Our exploration today is rooted in established principles of astrobiology, verifiable observations, and, crucially, the kind of evidence that makes scientists sit up and really take notice.
Okay.
It's all about scientific rigor and understanding the realistic inferences we can draw from what we see.
Okay, so where does this cosmic hunt even begin? What are the absolute must-haves? The ingredients for a planet to even be in the running for habitability, at least according to our current playbook.
Well, drawing from our one example of life here on Earth, there are a few key ingredients that consistently rise to the top of the list.
Okay, let's dive in. What's the first non-negotiable?
Liquid water. This one's fundamental, almost universally agreed upon in definitions of habitability.
Right.
Water's incredible ability to dissolve substances, its crucial role in biochemical reactions, its knack for keeping temperatures stable, it just makes it absolutely vital for life as we know it.
Yeah.
So, when we peer out at other star systems, the initial search often zeroes in on regions where liquid water could potentially persist, over significant timeframes. What are your thoughts on this? Does water seem like the obvious first requirement to you? Head to the comments and let us know.
Makes total sense. Water is life isn't just a saying down here. It really does seem like a cosmic truth.
Mm.
Okay, what's the next essential in this recipe for a living world?
An energy source. All known life requires some kind of power supply to fuel its internal machinery, basically just to sustain itself.
Uh,
On Earth, we see photosynthesis, obviously driven by sunlight, but we also see chemosynthesis in the dark depths of the ocean.
right near the vents.
Exactly. And even life thriving on geothermal energy or radioactivity deep underground. So this tells us that life might be quite adaptable in how it gets its juice.
So not every alien life form needs a suntan.
Okay.
Okay. And the third crucial ingredient.
Nutrients.
Yeah.
And the fundamental building blocks. Life needs access to essential elements. Think carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the CHNOPS elements.
The basics.
The basics. And it also needs the right conditions for these elements to combine into complex organic molecules, the very Lego bricks of life, if you will.
Yeah.
A planet's birth environment, its geology, that plays a big role in whether these elements are actually available. Interestingly, stars with a characteristic called metallicity.
Okay, what's that?
It basically refers to the abundance of elements heavier than hydrogen and helium in the star. Stars with higher metallicity are thought to be more likely to host rocky planets, which are, our primary focus in this quest for habitable worlds.
Okay, so liquid water, an energy source, and the right elemental building blocks.
Got it. Now, how do we translate that into actually pinpointing these potential oases out there? I keep hearing about this habitable zone. What's the real story behind that?
Yes, the circumstellar habitable zone, often abbreviated as HZ or sometimes called the Goldilocks zone. It's probably the most widely used concept for identifying regions around stars where life might have a chance.
Goldilocks zone. I love it. Not too scorching, not freezing cold. Just right.
Exactly. It's defined as the range of orbital distances from a star where a planet, if it has the right kind of atmosphere, could maintain liquid water on its surface.
Ah, the atmosphere is key.
Absolutely key. Yeah. It provides the necessary pressure and it can trap heat through the greenhouse effect, helping to keep temperatures within that life-friendly liquid water range. What kind of planets do you picture when you hear Goldilocks zone? Share your visualizations in the comments.
So a planet has to be in that orbital sweet spot,
Hmm.
but I guess it's not the same distance for every star. Absolutely not. The location and the width of the HZ, they aren't set in stone. They depend heavily on the properties of the host star itself.
Makes sense.
Brighter, hotter stars, they
Mm.
have habitable zones that are wider and located much farther away. Conversely, cooler, dimmer stars, like those very common M dwarfs we mentioned,
Yeah.
they have much narrower HZs that are really, really close to the star. And that close proximity, well, it comes with its own set of challenges we should probably get into.
Okay. And stars aren't these unchanging beacons either, are they? They evolve over time.
That's a really critical insight. Stars age, and
Uh,
generally they become more luminous as they do.
right.
This means the boundaries of their habitable zones also shift outwards over billions of years.
Mm.
So a planet that was once perfectly placed in the HZ could end up becoming too hot,
A runaway greenhouse, maybe.
potentially.
Yeah.
While another planet, maybe farther out, might eventually warm up enough to potentially support liquid water later in the star's life. This leads to the idea of the continuously habitable zone, or CHZ, which is the region where a planet could, in theory, maintain liquid water continuously over a significant chunk of the star's main sequence lifespan. We're talking billions of years for stars like our sun.
Right.
And the CHZ is particularly interesting when we think about the potential for complex life to evolve because, well, that took a very long time here on Earth.
Okay, so the habitable zone is our first big filter, a really useful starting point. But it's definitely no guarantee of life. A planet could be in the perfect orbital neighborhood, but still be, a barren wasteland for all sorts of reasons.
Precisely. A planet smack dab in the HZ might lack a substantial atmosphere. Maybe it got stripped away by intense stellar flares from its star, or its fundamental composition might just not be right. Maybe not enough rock, too much gas.
Uh-huh.
And conversely, as we're increasingly realizing, habitable environments might even exist outside the traditional H city. Think about those subsurface oceans we suspect on icy moons right here in our own solar system.
Europa Enceladus.
Exactly, kept liquid by internal heat, from tidal forces mostly. So while the HZ is a crucial starting point, it's really just one piece of a much larger, much more intricate puzzle. What kind of outside the box habitable zones can you imagine? Let's brainstorm in the comments.
Let's zoom in on the stars themselves then. It seems pretty obvious that the type of star a planet orbits would have a massive influence on its habitability.
It absolutely does. The host star is, well, it's the dominant force shaping any planetary system. Its light, its heat, its radiation, its gravity, everything.
We know our own sun, a G-type star, has been a pretty good landlord for what, 4.5 billion years, supporting a planet teeming with life. So are we mostly on the lookout for suns similar to ours, G-types?
G-type stars are certainly logical starting points. I mean, given our own successful example, n equals 1, though it may be.
Right.
However, they are less common than smaller stars, and they have a relatively shorter lifespan, maybe around 10 billion years total on the main sequence.
Okay. What about those smaller, cooler stars, the M dwarfs? You mentioned they're really common. They seem to be everywhere we look in the galaxy.
M dwarfs, or red dwarfs, yes, they are indeed the most abundant type of star in our galaxy, making up perhaps 70 to 80% of the entire stellar population.
Wow.
And they have incredibly long lifespans, potentially trillions of years in some cases, far longer than the current age of the universe.
Giants, okay.
However, their low energy output means their habitable zones are very, very close to the star.
Right, you mentioned that.
And planets in these tight orbits are often tidally locked, meaning one side always faces the star, the other is in perpetual darkness. That leads to extreme temperature differences between the day and night sides.
Challenging.
And perhaps even more significantly, many M dwarfs, especially when they're young, are prone to intense radiation and really powerful flares. These could wreak havoc on planetary atmospheres, stripping them away. Does the abundance of M dwarfs make you more optimistic or pessimistic about finding life out there? Share your thoughts in the comments.
So while they're plentiful and they live practically forever, they might also be pretty tough neighbors. Rough landlords, maybe.
Yeah.
What about the stars in between, like K-type stars? Orange dwarfs.
K-type stars, or orange dwarfs, yes.
Hmm.
They're often seen as a kind of Goldilocks star themselves, but potentially even better hosts for advanced life than either G or M types, some argue.
Really? Why is that?
Well, They're more numerous than G stars, are sun-likes, and they boast much longer, stable lifespans than G types, offering vast timescales for evolution to occur. Plus, they also tend to have lower levels of that harmful stellar activity compared to many M dwarfs.
Interesting. Okay, so the star is a huge piece of the puzzle, but the planet itself obviously has to have the right stuff too. Size and what it's made of, for instance.
Yeah.
We're mostly interested in rocky planets, right? Not gas giants?
That's the primary focus, yes. The search largely centers on rocky terrestrial type planets, similar in size and composition to Earth, or maybe slightly larger super Earths.
Right.
Gas giants like Jupiter or Saturn are generally considered unlikely to offer habitable surface conditions, although maybe their moons could be interesting.
Another conversation, maybe.
Right. But determining a planet's density, which we can figure out from its mass and its radius if we can measure both, gives us crucial clues about its bulk composition. Is it mostly rock and metal, or does it have a lot of lighter stuff like water or gas?
And the atmosphere, there's got to be a major player. We keep coming back to it.
Absolutely essential. A suitable atmosphere provides the necessary surface pressure for liquid water to exist. It regulates temperature through the greenhouse effect. And importantly, it acts as a shield against harmful radiation from the star and from space.
Yeah.
The specific mix of gases, the thickness of the atmosphere, these are critical.
Hmm.
And the potential for a planet to lose its atmosphere over time due to strong stellar activity or just having weak gravity, that's a significant concern for long-term habitability. What kind of alien atmospheres do you imagine might exist? Let your creativity flow in the comments.
I also hear people talk about magnetic fields,
Yeah.
like Earth has. Are those important for a planet's ability to support life?
It's thought to be quite important, yes, although we can't directly detect them on exoplanets just yet. A global magnetic field, like Earth's magnetosphere, acts as a protective bubble.
Okay.
It deflects the stellar wind, that constant stream of charged particles from the star, and helps prevent the atmosphere from being stripped away over vast timescales. This could be particularly crucial for planets orbiting those more active M dwarf stars we talked about.
Makes sense. And what about the planet's own internal activity? Things like volcanoes, plate tectonics, do they factor into habitability?
Oh, absolutely. Those internal processes can significantly influence a planet's long-term habitability. Plate tectonics on Earth, for example, plays a key role in regulating our climate over geological timescales through the carbon cycle. And it also helps in recycling essential nutrients, bringing them up from the interior. More massive rocky planets, super Earths, might retain their internal heat for longer, potentially sustaining geological activity and its beneficial effects for longer durations than Earth has.
Wow. Okay, it's becoming really clear that habitability isn't just one thing. It's this intricate cosmic recipe with a whole bunch of ingredients and conditions that all have to line up. But scientists are also starting to think beyond just Earth-like scenarios, right? I've heard whispers of some more exotic possibilities.
That's where things get really exciting, I think, where our understanding starts to expand beyond our own familiar world. While the search often begins with finding Earth twins or something close, research is increasingly exploring a much wider range of potentially habitable environments.
Like what you mentioned, oceans hidden beneath icy surfaces earlier,
Yeah.
like on Europa.
Exactly. We know these exist, or strongly suspect they exist, on moons right here in our own solar system, kept liquid by internal heat generated mostly by tidal forces from their giant planets. The same could very well be true for exoplanets, maybe rogue planets without stars, or even exomoons orbiting gas giants far beyond the traditional stellar habitable zone. These subsurface oceans could potentially harbor life completely independent of surface conditions, maybe clustered around hydrothermal vents like on Earth. What kind of life do you think might thrive in a dark subsurface ocean on another world? Dive into the comments with your ideas.
That's fascinating. And these Haitian worlds I've been reading about, what's the buzz around those? Sounds like something out of science fiction.
Haitian worlds, yes, they're a relatively new and truly intriguing concept. These are envisioned as planets that are larger than Earth, maybe mini Neptunes, but with deep global oceans beneath hydrogen-rich atmospheres.
Hydrogen atmospheres. Isn't hydrogen very light?
It is, but on a massive enough planet, it can be retained. And despite potentially high surface pressures and temperatures that might seem extreme to us, the conditions within the ocean could be surprisingly suitable for microbial life. Their habitable zones might even be broader than those for Earth-like planets because the thick atmosphere helps keep things warm.
Interesting.
K218b is a leading candidate that's generating a lot of interest in this area, which we can talk more about.
Wow, so life might be lurking in some pretty unexpected cosmic corners. And I've also heard talk about superhabitability. Is that actually a thing? Could a planet be better than Earth for life?
It is a fascinating concept that some research is exploring, yes. The idea is that certain exoplanets might possess conditions that make them even more conducive to life or perhaps more complex life than Earth is.
That's
Well, factors like orbiting a very stable K-dwarf star, maybe being slightly warmer than Earth on average, having more extensive shallow ocean coverage, or perhaps a slightly denser atmosphere. Theoretically, these could combine to make a planet even more hospitable to life's flourishing than our own world. Can you imagine a world even more alive than Earth? What would that look like? Share your visions in the comments.
That's mind-bending. But what about complex life, like animals? You mentioned that. Would the requirements be different for them compared to just, say, microbes?
It seems likely. Studies suggest that the environmental requirements for complex animal-like life might be more stringent than for simple microorganisms. For example, high concentrations of certain gases like carbon dioxide, which might be perfectly fine or even necessary to keep a planet warm enough for microbial life at the outer edges of a habitable zone, could actually be toxic to complex life as we understand it. This hints at a potentially narrower habitable zone for complex life.
So habitability isn't just a simple yes or no, like flipping a switch. It's this whole spectrum of possibilities,
Exactly.
ranging from maybe single-celled organisms surviving in really bizarre environments, all the way up to potentially super habitable worlds teeming with complex life we can barely imagine.
Precisely. And understanding the spectrum requires us to consider the specific types of life we're talking about. The very definition and how we measure habitability are active and evolving areas of research, constantly being refined as we learn more about life on Earth and gather new data from the ever increasing number of exoplanet observations. This makes you wonder, doesn't it? What if the most common form of life in the universe isn't anything like what we expect? Let's ponder that in the comments.
It's truly incredible to contemplate all the diverse ways life might find a foothold across the cosmos. Now, okay, how are we actually finding these distant worlds and trying to figure out if they might be habitable? What are the main tools and these ingenious techniques we're using?
Well, the discovery and characterization of exoplanets rely on a suite of incredibly sophisticated observational techniques and really powerful telescopes, both on the ground and orbiting up in space. The field has just exploded with progress in recent decades.
Okay, so what are some of the key methods we use to actually detect these planets lurking around distant stars? They're so far away and faint.
One of the most successful methods, the one that found thousands of planets, is called transit photometry.
Okay.
This involves carefully, precisely monitoring the brightness of a star over time. If a planet happens to pass directly between the star and us here on Earth, it blocks a tiny, tiny fraction of the starlight.
Like a mini eclipse.
Exactly, causing a periodic dip in the star's measured brightness. The amount of dimming tells us something about the planet's size relative to the star, and the time between these dips reveals its orbital period, how long it takes to go around. Telescopes like Kepler and now TESS have been absolute workhorses using this technique. Can you imagine detecting a tiny shadow of another world crossing a star trillions of miles away? What does that evoke for you? Share your feelings in the comments.
It's like spotting a minuscule fly crawl across a giant stadium light from miles and miles away. It's incredible. What's another clever way we find exoplanets?
Another key technique is the radial velocity method, sometimes called Doppler spectroscopy or the wobble method.
The wobble method.
Yeah, this method detects planets indirectly by observing their gravitational influence on their host star. As a planet orbits, its gravity causes the star to wobble ever so slightly back and forth along our line of sight.
Huh.
This wobble results in tiny shifts in the star's light spectrum, a blue shift as the star moves slightly towards us, and a red shift as it moves slightly away. By precisely measuring these cyclical shifts, we can infer the presence of the planet, determine its orbital period, and even estimate its minimum mass based on how strong the wobble is.
So we're not seeing the planet at all. We're seeing the star dance because of the planet.
We're feeling its gravitational tug on its star,
Huh.
exactly. What do you think is more amazing, seeing a planet's shadow or feeling its gravitational pull across vast distances? Let's debate in the comments.
That's brilliant.
But yeah.
Are there ways to actually capture images of these distant worlds to actually see the planet?
Yes, that's called direct imaging. This involves capturing actual photons of light that originated from the exoplanet itself, either starlight reflected off its atmosphere or clouds, or its own thermal glow, its heat.
Wow.
It's an incredibly difficult feat, as you can imagine, because planets are so incredibly faint compared to their brilliant host stars, and they often orbit very close by.
The firefly next to the searchlight problem.
Exactly that. We need advanced techniques like coronagraphs or starshades to block out that overwhelming starlight. But it offers the potential for really detailed characterization, including analyzing the planet's atmosphere directly by looking at the colors in its light. The James Webb Space Telescope has already successfully captured direct images of some exoplanets, usually large ones far from their stars. Imagine seeing a faint pinprick of light that is another world. What would be the first thing you'd want to know about it? Head to the comments.
That must be unbelievably challenging. What other ingenious methods do astronomers have in their toolkit? Are there
Oh,
others?
yes. There's gravitational microlensing, which uses the bending of light by gravity, as predicted by Einstein, to reveal the presence of planets, even ones very far away or not orbiting any star at all. Astrometry involves precisely measuring the position of a star on the sky over long periods to see if it's wobbling side to side due to an orbiting planet's gravity, not just back and forth. And timing variations look for slight deviations in the predictable timing of periodic astronomical signals, like from pulsars caused by the gravitational pull of unseen planets disrupting those signals. Each method has its own strengths and limitations, and each is more effective at finding certain types of planets in certain types of orbits.
It sounds like just finding the planets is a monumental achievement in itself. But once we've spotted one, how do we even begin to figure out what it's actually like, whether it could be a place where life could exist?
That's where the crucial step of characterization comes in. And often, a powerful approach is to combine data gathered from different detection methods.
How so?
For example, if we know a planet's radius from the transit method, how big it is, and we can estimate its mass from the radial velocity method, how heavy it is, we can then calculate its average density.
Mass divided by volume.
Exactly. And that density gives us a vital clue about its bulk composition. Is it primarily rocky like Earth? Is it a fluffy gas giant like Jupiter? Or maybe something else entirely, like an icy world or one of those Hyson planets?
And then there's studying the light itself using spectroscopy, right?
Yeah.
That seems key for atmospheres.
Exactly. Analyzing the light that comes from or interacts with an exoplanet is the key to unlocking the secrets of its atmosphere. In transmission spectroscopy, which works for transiting planets,
Okay.
we study the starlight that passes through the planet's thin atmospheric limb as it crosses in front of the star. Different molecules in the atmosphere absorb specific wavelengths, specific colors of light.
Like a barcode.
Precisely. It leaves a unique fingerprint or barcode in the spectrum that reveals what the atmosphere is made of: water vapor, methane, carbon dioxide, etc. We can also analyze the light directly emitted or reflected by the planet using direct imaging or phase curve analysis to learn about its temperature and other atmospheric properties. Atmospheric spectroscopy is really our primary tool right now in the search for those telltale signs of life biosignatures. Can you imagine deciphering the atmosphere of another world just by analyzing its light? What kind of atmospheric surprises do you think we might find? Let's speculate in the comments.
It's absolutely mind-blowing how much information we can extract from these tiny pinpricks of light that have traveled trillions upon trillions of miles across the cosmos.
Yeah.
It sounds like we have some truly incredible instruments and ongoing missions that are really propelling this field forward.
Absolutely. We've had groundbreaking missions like Hubble and Spitzer that laid essential groundwork, really proved these techniques could work. Kepler was a revolution, just showing us how utterly commonplace exoplanets actually are in the galaxy.
Yeah, Kepler changed everything.
It really did. And now we have the current workhorses like TESS, the Transiting Exoplanet Survey satellite, which is surveying nearby bright stars all over the sky, and numerous ground-based radial velocity surveys that are constantly pushing the boundaries of precision, finding smaller and smaller planets.
And of course, the James Webb Space Telescope, JWST. It feels like that's a real game changer in this cosmic quest, isn't it?
It truly is. JWST's huge mirror and its exceptional sensitivity, particularly in the infrared part of the spectrum where molecules have strong signatures, allow for unprecedented detail in exoplanet spectra.
Right.
It's already providing crucial data on the atmospheres of planets, including some in potentially habitable zones, searching for the presence of water, carbon-based molecules, and maybe, just maybe, those tantalizing potential biosignatures.
It's clear that we're building this impressive arsenal of tools and accumulating a wealth of knowledge in the search for other worlds. Now, with thousands of exoplanets discovered, which ones are currently considered the most promising candidates, the front runners in the race for potential habitability?
Yeah, Identifying the most promising candidates requires a careful process of prioritization. We have to take into account factors like the planet's size and estimated mass. Is it likely rocky? Its orbital location, is it in the habitable zone? The characteristics of the host star itself, is it stable? And importantly, is the system actually amenable to detailed atmospheric study with our current or near future telescopes?
You've highlighted a few in our prep that are really generating excitement. TRAPPIST-T1e, Proxima Centauri b, K2-18b, and TOI 700d. These feel like the current rock stars of the potentially habitable exoplanet scene, wouldn't you say?
They are certainly among the most frequently discussed and intensely studied right now, yes, and each one presents a unique set of intriguing possibilities, but also its own distinct challenges.
Okay, let's start with TRAPPIST-T1e. That's part of that incredibly fascinating system, right? With the 7 Earth-sized planets all orbiting a single, tiny, cool star. It's like a cosmic miniature solar system.
TRAPPIST-1 is indeed an ultra-cool red dwarf star, much smaller and cooler than our sun, and it hosts this remarkable family of 7 known Earth-sized planets, all orbiting incredibly close to their star, closer than Mercury orbits our sun.
Wow.
3 of them, planets E, F, and G, reside within the star's conservatively defined habitable zone. TRAPPIST-2-1e, in particular, gets a similar amount of stellar energy as Earth does from the sun, and its measured density suggests it could be a rocky world, maybe with a significant amount of volatile compounds like water. It's a prime target for JWST to try and characterize its atmosphere. But orbiting so close to a red dwarf brings its own set of challenges, doesn't it? What kind of extreme conditions do you think planets in such tight orbits might face? Let's brainstorm in the comments.
Right, but that star, TRAPPIST-1, it's known to be quite active, isn't it? Lots of stellar flares erupting pretty often.
Yeah.
How does that kind of intense activity potentially impact the habitability of its planets?
That's a really significant concern, probably the biggest one for the TRAPPIST system. The frequent and sometimes incredibly powerful flaring activity of a TRAPPIST-1 poses a major challenge to the potential for life on its planets. These flares could potentially erode or even completely strip away planetary atmospheres over billions of years.
Ouch.
Early observations with Hubble on the inner planets ruled out cloud-free atmospheres dominated by hydrogen, but denser atmospheres, maybe rich in CO2 or water, are still a possibility. Extensive theoretical modeling is underway, trying to figure out if habitable surface conditions with liquid water could somehow be maintained under various atmospheric compositions, despite that constant bombardment from stellar flares. JWST observations are ongoing right now, and they are absolutely crucial to helping us answer these critical questions.
Okay. Next up is Proxima Centauri b.
Mhm.
This one feels particularly exciting because it's orbiting the nearest star to our own sun, our cosmic next-door neighbor.
Proxima Centauri b is indeed our closest known exoplanet neighbor, just over 4 light years away. It's a planet with a minimum mass similar to Earth's, orbiting within the habitable zone of Proxima Centauri, which, like TRAPPIST-1, is also an active red dwarf star.
Another red dwarf.
Yes, and so the big question mark hanging over Proxima b is once again its atmosphere. Given Proxima Centauri's frequent and powerful flares, possibly even worse than TRAPPIST-1's, can Proxima b retain a substantial atmosphere over the long haul?
Yeah.
Models suggest that atmospheric loss could be significant, potentially stripping away an Earth-like atmosphere very quickly unless maybe it has a strong planetary magnetic field, which could offer crucial protection.
Do we know if it has one?
We don't know. Climate models have explored various scenarios, and some indicate that liquid water could potentially exist on the surface, perhaps in the regions near the terminator, the line between day and night if it's tidally locked. But we currently lack any direct observational evidence of its atmosphere. It's a very challenging target. Wouldn't it be incredible if our nearest stellar neighbor hosted a habitable world? What are your hopes and concerns about Proxima b? Share your thoughts in the comments.
Then there's K2-18b, which has been generating a huge amount of buzz recently as a potential Hyson world. You mentioned these earlier. It sounds like a truly alien kind of planet.
K2-18b is fascinating. It's a super Earth, maybe 8 times the mass of Earth, orbiting a red dwarf star within its habitable zone. What makes it particularly intriguing is its size and its surprisingly low density,
Meaning?
meaning it almost certainly possesses a substantial water envelope, maybe a deep global ocean, and a hydrogen-rich atmosphere, those defining characteristics of a Hyson world. Observations with the James Webb Space Telescope have detected methane and carbon dioxide in its atmosphere, which is interesting. But they also found a notable absence of ammonia, which actually aligns well with the predictions for Hyson planets, where ammonia would be expected to dissolve into the water ocean below.
Wow.
And even more tantalizingly, initial JWST data hinted at the possible presence of dimethyl sulfide, or DMS.
DMS, what's that?
It's a molecule primarily produced by phytoplankton in Earth's oceans, and it's considered a significant potential biosignature because it doesn't have many known large-scale abiotic sources.
Whoa.
Now, very recently, a more detailed analysis of JWST data has provided even stronger evidence for either DMS or potentially a closely related sulfur-containing compound at pretty high abundances in its atmosphere. This
Oh.
is incredibly exciting.
Yeah.
Because these molecules are relatively short-lived in an atmosphere, finding them could suggest a possible continuous biological source actively replenishing them. However, and this is a big however, it is absolutely crucial to remember that more research, more observation, more modeling is needed to definitively rule out any non-biological explanations for these findings. We need to be cautious. But the possibility of detecting a potential biosignature on a Hyson world, it's truly groundbreaking stuff. What were your first thoughts when you heard about the potential DMS detection on K218b? Let's discuss in the comments.
The potential biosignature. That is monumental. But yes, as you rightly pointed out, got to proceed with caution, got to be rigorous, rule out other possibilities. Okay, finally, let's talk about TOI 700D. This one was discovered by the TESS mission, which you mentioned has been a real planet finding machine.
That's right. TOI 700D is an Earth-sized planet orbiting a remarkably quiet M dwarf star within its habitable zone. And this quiet nature of its host star is a really significant advantage for its habitability prospects. It means it likely faces far fewer of those atmosphere-stripping flares compared to planets around TRAPPIST-1 or Proxima Centauri.
Oh, good landlord.
Potentially a much better landlord, yes. Climate models suggest that TOI 700D could potentially maintain temperate surface conditions suitable for liquid water under a variety of plausible atmospheric compositions. However, actually characterizing its atmosphere observationally presents a significant challenge.
Also.
The predicted atmospheric signals, the little dips in starlight during transit, are expected to be very, very faint, likely below the current detection capabilities of even the powerful James Webb Space Telescope.
Oh,
So, while it looks quite promising from a theoretical standpoint, we'll likely need future generations of even more powerful observatories to truly probe its atmosphere and see what's going on there. Of these four leading candidates, which one excites you the most and why? Head to the comments and share your cosmic enthusiasm.
it's absolutely captivating to hear about these leading candidates, each with its own unique story and tantalizing potential. It really underscores just how incredibly diverse these exoplanetary systems are. But finding a potentially habitable environment is really just the first chapter, isn't it? The ultimate, incredibly ambitious goal is to find actual evidence of life itself, those elusive biosignatures.
Exactly. Pinpointing a potentially habitable environment is the critical first step, sets the stage. But the grand prize, the ultimate goal for many in this field, is finding concrete, unambiguous evidence of past or present life beyond Earth. And since we can't exactly send probes to all these fascinating worlds anytime soon,
Not yet, anyway.
not yet, the search is heavily focused on remotely detectable biosignatures, signs of life we can spot from light years away.
So what exactly constitutes a biosignature? What kind of telltale signs are we actively searching for in the vastness of space?
Well, a biosignature is broadly defined as any object, substance, pattern, feature, or process whose origin strongly suggests a biological agent. The crucial part is that it's highly unlikely to be formed through purely non-biological or abiotic processes under the specific conditions of that particular planet.
Okay.
In the context of exoplanet science, we primarily concentrate on atmospheric biosignatures, so gases in a planet's atmosphere that are produced or significantly influenced by biological activity, and maybe surface biosignatures, large-scale features on the planet's surface caused by life that alter how the planet reflects light.
Okay, let's talk atmosphere first. What are some of the key atmospheric biosignature candidates that scientists are particularly eager to detect?
Oxygen, O2, and its derivative ozone, O3, are definitely high on the priority list. Why? Because oxygen is so abundant in Earth's atmosphere, about 21%, largely due to the ongoing process of photosynthesis by plants and algae. However, we've come to understand over the years that oxygen can also be produced abiotically, without life, under certain conditions, like on a wet planet losing hydrogen to space around a very active star. So, oxygen is not a definitive solo signature on its own. It needs context.
Okay, interesting. What else?
Methane, CH4, is another molecule of interest. It's produced by some forms of microbial life on Earth, methanogens. But, again, it also has significant non-biological sources like geological activity or processes in planet formation.
So simply detecting oxygen or methane in an exoplanet's atmosphere wouldn't automatically mean we've hit the cosmic jackpot and found ET.
That's precisely right. This realization, the problem of false positives, has led to a greater emphasis on the concept of chemical disequilibrium.
Is this equal?
Yeah, basically looking for combinations of gases in an atmosphere that shouldn't coexist in significant amounts unless there's a continuous biological source actively replenishing them because they normally react with each other and disappear. The classic example is the simultaneous presence of lots of oxygen and lots of methane in Earth's atmosphere. Those two gases want to react.
Okay.
Finding them together strongly suggests something is constantly producing both. We're also increasingly interested in more complex molecules like that dimethyl sulfide, DMS, we talked about with K218b, which seem to have fewer known, robust, non biological origins, making them potentially stronger candidates.
Okay, that makes sense. And what about surface biosignatures? What kind of large-scale signs of life might we be able to detect from light years away? It seems even harder.
It is harder, but not impossible. The most commonly discussed example is the vegetation red edge, or VRE.
The what's now?
The vegetation red edge. Photosynthetic pigments on Earth, like chlorophyll in plants, strongly reflect near infrared light while absorbing visible red light. This creates a sharp increase, an edge in the reflectance spectrum of our planet right at the boundary between red and infrared wavelengths. Detecting a similar distinct spectral feature, a sharp edge like that, on an exoplanet could potentially indicate widespread surface photosynthesis, although we have to remain open to the possibility that alien life might utilize completely different pigments with different spectral signatures, maybe making a blue edge or something else entirely.
It sounds like interpreting these potential biosignatures is an incredibly complex puzzle. How do scientists even begin to determine if something is truly a sign of life and not just some bizarre, non-biological chemical process playing tricks on us?
Context is absolutely paramount. You said it's a puzzle. A potential biosignature cannot be evaluated in isolation. We need to thoroughly understand the entire environmental context of the planet, meaning the type and activity level of its host star, its precise location within the habitable zone, its overall size, its density, its likely bulk composition, and crucially, the presence and abundance of other gases in its atmosphere. What else is there?
Right.
We also have to carefully evaluate the reliability, the potential longevity, and the detectability of any proposed biosignature. And increasingly, scientists are employing sophisticated probabilistic frameworks, Bayesian analysis, for example, to try and quantify the level of confidence in a biosignature detection, meticulously taking into account all the available evidence and the likelihood of any plausible non-biological explanations. It's about weighing the evidence.
So the really tricky part is telling the difference between a world that is truly alive and one that just happens to have some interesting life-mimicking chemistry happening, avoiding those dreaded false positives.
Exactly. Abiotic mimics, or false positives, are a major focus of research right now. For example, as we discussed, oxygen can be generated without life through photolysis, the splitting of water vapor in the upper atmosphere by stellar UV light, followed by the escape of the lighter hydrogen into space, leaving oxygen behind.
Okay.
We need to look for other accompanying clues, like the absence of certain other gases or specific atmospheric conditions, to differentiate that abiotic oxygen from biologically produced oxygen. Similarly, there are known non-biological pathways to produce methane, maybe even more complex organic molecules under specific planetary conditions like serpentinization or atmospheric chemistry.
So it takes a village of scientific discipline.
Absolutely. That's why a comprehensive understanding of planetary science, atmospheric chemistry, geology, stellar physics, it's all utterly crucial in this endeavor. What kind of unexpected non-biological processes do you think might mimic signs of life? Let your imagination run wild in the comments.
And then there's the flip side of the coin, right? The possibility of false negatives. Life might actually exist on a planet, but for some reason we don't detect any clear signs of it.
That's also a very real possibility that definitely keeps researchers awake at night. Life might exist, say, in subsurface environments, like those hidden oceans we discussed,
Right, under the ice.
and not significantly alter the planet's global atmosphere in ways we can easily detect from light years away. Or life might be producing biosignature gases, but the specific planetary conditions, maybe atmospheric chemistry or circulation, prevent them from accumulating to detectable levels in the observable part of the atmosphere.
Mm.
Or perhaps, most humbling of all, alien life might utilize completely different biochemical processes that don't produce the specific biosignatures we are currently designed to look for, based on our Earth centric understanding of life.
Life, but not as we know it.
Precisely. And of course, maybe the simplest explanation for a non detection is that our current instruments might simply lack the necessary sensitivity to detect faint traces of even familiar biosignatures on distant small worlds.
It seems like definitively confirming a biosignature and, announcing to the universe
Yeah.
and ourselves that we found life beyond Earth is going to require incredibly robust evidence, like multiple independent lines of evidence,
Mhm.
all pointing to the same conclusion,
Absolutely.
and a painstaking process of carefully ruling out all those potentially misleading non-biological explanations first.
Absolutely. The consensus in the field is increasingly focusing on the search for multiple biosignatures detected simultaneously, particularly those that are in that state of significant chemical disequilibrium we talked about, or for the detection of complex molecules that are considered much less likely to arise from non biological origins.
Mhm.
There's also growing interest in developing agnostic biosignatures methods, focusing on detecting unexpected complexity or patterns in the data rather than specifically searching for terrestrial like biochemical markers. Trying to find something weird that screams life without presupposing what that life looks like.
Interesting.
Ultimately, building a true.
This has been an absolutely mind-opening overview of the exciting search for habitable exoplanets and those tantalizing, tricky biosignatures. It's so clear that this is a field that is not just active, but rapidly evolving. New discoveries, new insights seem to be emerging all the time. So, looking ahead, what does the future hold for this incredible quest? What are the next big missions and cutting-edge technologies that are going to help us finally try and answer this profound, age-old question of whether we are truly alone in the cosmos?
The coming decades hold immense promise for significant breakthroughs. We really are entering a new era. We have a suite of next generation missions planned or already underway that are specifically designed to push the boundaries of exoplanet discovery and crucially detailed characterization.
Okay, tell me about some of these truly exciting missions that are on the horizon. What should we be looking out for?
Well, ESA's Plato mission, the European Space Agency's mission, scheduled for launch around 2026, is specifically designed to find and thoroughly characterize Earth sized planets located within the habitable zones of Sun like stars. It's going to be looking for transits around brighter stars than Kepler did.
Okay.
It will provide incredibly precise measurements of planet radii, and when combined with follow up observations from ground based telescopes to get the mass, it will give us highly accurate planet densities for potentially habitable worlds. Plato will also help us understand the ages of these host stars, which is important for habitability.
Cool. What else?
Then there's ESA's Ariel mission, slated for launch around 2029. Ariel will focus specifically on conducting a large scale survey of the atmospheres of a diverse sample of known exoplanets, maybe up to 1,000 of them. It will use infrared transit spectroscopy to probe their composition and thermal structure.
1,000 atmospheres.
A big survey, yes. And NASA's Nancy Grace Roman Space Telescope, formerly WF-EARTH, which is preparing for launch later this decade, will conduct a massive microlensing survey from space. That's expected to discover a wealth of new planets, including maybe Earth-mass ones farther from their stars. Roman will also carry a sophisticated coronagraph instrument as a technology demonstration to test and advance high-contrast direct imaging techniques for future missions. These missions are poised to deliver just a treasure trove of new data. Which of these upcoming missions are you most excited about and why? Share your cosmic hopes in the comments.
And looking even further into the future, I keep hearing about this really ambitious concept called the Habitable Worlds Observatory. That sounds like a real game changer, potentially the one to find life.
The Habitable Worlds Observatory, often referred to as HWO, yes, that is NASA's next envisioned flagship Great Observatory, following on from Hubble, Spitzer, Chandra, and Webb. It's being designed specifically from the ground up to directly image potentially habitable Earth-sized exoplanets orbiting sun-like stars.
The Holy Grail.
It's the Holy Grail, yes. And to meticulously analyze their atmospheres in the search for those elusive biosignatures. It will employ cutting edge, high contrast imaging technology, likely a combination of an internal coronagraph and possibly an external starshade, to effectively suppress the overwhelming light of the host star by factors of billions or even tens of billions.
Wow.
This will enable the spectral characterization of these incredibly faint planetary companions. The primary science goal, as currently envisioned, is to survey approximately 160 nearby sun-like stars and directly detect and study the atmospheres of at least 25 potentially habitable worlds.
25 Earth analogs.
At least 25 potentially habitable zone rocky planets around sun-like stars, yes. The Habitable Worlds Observatory represents a truly dedicated effort aimed squarely at achieving that ultimate goal of directly imaging Earth-like planets and searching for compelling signs of life. It's an incredibly ambitious undertaking, probably launching sometime in the 2040s, but the potential reward finally answering that fundamental question is truly immeasurable. What kind of discoveries do you dream the Habitable Worlds Observatory might make? Let your imagination soar in the comments.
That's an incredible and inspiring goal. And what about advancements happening right here on Earth? In our ground-based astronomy capabilities, are they keeping pace?
Oh, absolutely. Ground based astronomy is also entering a new golden age with the development of the Extremely Large Telescopes, or ELTs.
Right, these giant telescopes being built.
Exactly. Facilities like the Giant Magellan Telescope and the 30-meter telescope in the U.S. lead sphere, and the European Southern Observatory's Extremely Large Telescope, simply called the ELT. These colossal facilities will boast unprecedented light collecting power with mirrors tens of meters across and exceptional spatial resolution thanks to advanced adaptive optics.
What will they let us do?
They will allow for incredibly detailed characterization of exoplanet atmospheres through high-resolution spectroscopy, teasing apart atmospheric constituents in much greater detail, and potentially even direct imaging of some of the nearest and perhaps larger potentially habitable planets, especially around M dwarfs. We're also witnessing continued and rapid progress in refining the precision of the radial velocity technique from the ground, pushing its limits to detect even smaller, truly Earth-mass planets orbiting within the habitable zones of their stars. The synergy between these ground-based giants and the space-based observatories like Webb, Ariel, Plato, and eventually HWO is going to be absolutely crucial in the years and decades to come.
It sounds like there are still some really significant technological hurdles that need to be overcome to achieve these ambitious goals, especially when it comes to directly imaging those faint, Earth-like planets orbiting their much brighter stars. That contrast problem sounds immense.
Absolutely. Achieving the extreme contrast ratios necessary, separating the faint planet light from the blinding starlight, demands major breakthroughs in starlight suppression technologies, like those advanced coronagraphs and potentially large formation-flying starshades. We also need incredibly sensitive detectors, capable of counting individual photons and ultra-stable spectrographs to be able to detect and analyze the incredibly faint signals emanating from the atmospheres of these small, rocky worlds.
And the interpretation.
And of course, we'll need increasingly sophisticated data analysis techniques, powerful computational modeling, and ever more accurate climate and photochemical models to correctly interpret the gathered data and confidently distinguish genuine biosignatures from those potential false alarms we talked about. It's a multifaceted challenge.
It really sounds like it's an international and collaborative effort, isn't it?
Yeah.
This profound search for life beyond our own small planet. It's not just one country or one agency.
It is indeed. It requires sustained and robust collaboration between space agencies across the globe, NASA, ESA, and others. It involves the diverse and dedicated international scientific community, from astronomers and planetary scientists to biologists and chemists, and it needs ongoing investment in both cutting-edge technology development and fundamental scientific research to understand the context.
Yeah.
It's a long-term endeavor, definitely a marathon rather than a sprint. But the potential payoff, finally answering that fundamental question of whether we are truly alone in this vast universe, is so immense, so profound, that it's worth every bit of effort and ingenuity we can possibly muster. What does this global, collaborative nature of the search for life say about humanity, do you think? Share your thoughts in the comments.
So to bring things toward a close for this deep dive, where do we stand in our cosmic quest right now? We've discovered thousands of exoplanets, literally thousands, including a tantalizing number of promising candidates residing within the habitable zones of their stars. We're even beginning to peer into the atmospheres of some of these distant worlds.
That's a perfect summary. The field has made just extraordinary leaps forward in a relatively short amount of time, maybe 30 years since the first confirmed discoveries. We're transitioning now from simply finding exoplanets, cataloging them, to the much more nuanced and challenging task of actually characterizing them in detail and rigorously assessing their potential to harbor life. The James Webb Space Telescope is already providing us with our first real, detailed glimpses into the atmospheres of worlds like K218b, which, as we discussed, has offered some truly intriguing hints of potential biosignatures.
But, as we've stressed, no definitive smoking gun proof of habitability or, even more excitingly, of life itself has been found just yet. It's still a very careful, evidence-based scientific process. No jumping to conclusions.
Exactly. There are still significant uncertainties surrounding each of the current leading candidates, and the interpretation of any potential biosignatures remains a formidable scientific challenge that requires extreme care. We need to be absolutely rigorous in our efforts to rule out any and all plausible non biological explanations for the observations we make before claiming something as extraordinary as extraterrestrial life.
And there are still so many fundamental unanswered questions that are driving future research and exploration, right?
Hmm.
Like the actual prevalence of rocky, habitable zone planets throughout the galaxy. Are they common? Are they rare? The complex processes that govern how planets form and retain their crucial atmospheres over billions of years. The incredible diversity of exoplanet atmospheres we're only just beginning to uncover. The ultimate reliability and unambiguous detection of biosignatures, and even the very fundamental question of what other forms life in the universe might potentially take, if it exists at all. It's a vast and exciting frontier of knowledge.
Indeed. But the path forward, while certainly challenging, is becoming increasingly clear. We will continue to explore with our current powerful suite of instruments, squeezing every bit of information out of them, and we are actively developing even more advanced and capable ones for the decades to come. The Habitable Worlds Observatory represents that dedicated, ambitious effort aimed squarely at achieving the ultimate, potentially transformative goal of directly imaging Earth like planets and searching their atmospheres for undeniable signs of life. It's a truly profound quest, one that speaks to our deepest curiosity about our place in the universe.
It is an absolutely incredible quest, and while we don't have the ultimate answer yet, the coming decades hold such immense potential for groundbreaking new discoveries that could literally forever change our understanding of the cosmos and our place within it. It really makes you wonder, doesn't it? What extraordinary secrets are just waiting to be uncovered out there among the stars? What are your final thoughts on this grand cosmic adventure we're all a part of, even just by looking up and asking the question?